So, after we've spent the last couple of weeks doing some really hard stuff, or at least stuff that I think is really difficult, the good news is that today we're going to finally get back to some stuff that, well, I'm not going to say it's easy, but at least to me, I find it a little bit simpler to deal with in a lot of ways than the stuff that we've been doing. So, I hope that you'll agree with me. If you don't, that's fine. Different people find different things hard or easy, but to me, today's topic is going to feel like a little bit of a break after the difficult material that we've been covering. What we're going to be talking about here is, what do you do if you want to do a definite integral, but you can't set it up as a Riemann sum for some reason? And there's a few different reasons why that could happen. So I want to kind of illustrate one of those examples now. What would happen if I needed to do, say, an integral, but the interval over which I'm doing it isn't a bounded interval? So what if I needed to go from, let's say, 1 up to infinity of 1 over x squared dx? Like, this is a sensible question to kind of ask, okay? It really is something that makes a lot of sense mathematically in various contexts. We want to talk about what this integral would be. We want to be able to integrate something across intervals that aren't necessarily bounded. But we can't do that in terms of Riemann sums. The reason is because you can't take the interval, why am I putting a 0 there? I'm sorry, 1 up to infinity. You can't just split that into a finite number of equally spaced intervals. It's an infinitely long interval. So you can't do this via Riemann sums. It's just not possible to make sense of it that way. Another situation where we might have problems with Riemann sums is where, instead of the interval being unbounded, we might have the function be unbounded. So what if I wanted to do something like the integral from 0 up to 1 of 1 over the square root of x dx? Well, the problem here is that in this case, the interval is just fine. The interval just goes from 0 to 1, so there's no problems there. But the problem is that the function itself is unbounded. As we come in towards 0, it gets up arbitrarily high. Now that means we can define some Riemann sums, but the Riemann sums themselves are unbounded, because whatever I do on this first rectangle, so to speak, I can make this as large as I want to, and it messes up the Riemann sums. The conclusion is that we really cannot define these kinds of definite integrals in terms of Riemann sums. And this is a flaw in Riemann's whole approach to integration, okay? This is not like, I don't want to say it's unavoidable. It is unavoidable in his approach, but it's not like a fundamental problem in what should integrals mean. It's really more that the Riemann sum definition of the integral only makes sense for bounded functions on bounded intervals. What do I mean by bounded? I mean that they have they have a lower bound and an upper bound. So the function is sandwiched between some least quantity and some greatest quantity. The interval is also sandwiched between some lower bound and some upper bound. Okay, so in those cases, the Riemann sum definition makes a lot of sense, but it doesn't necessarily make sense in other situations. And the question we want to ask is, can we still make sense of these kinds of integrals? Well, there are two ways that you could go about doing this. The first way is we could try a different approach entirely to the definition of the integral. So instead of taking Riemann sums, we could try defining integration in a completely different way. This is actually one of the ways that mathematicians deal with the problem. There is an alternative approach to integration, which is known as Lebesgue integration. It's spelled, French name. So, French spelling, it looks a bit odd to those of us who are native English speakers. It looks like Lebesgue or something, but it's pronounced Lebesgue. And his method is actually better than Riemann's in two different ways. One of them is that it sort of doesn't have as much of a problem here, although it still has problems. So there's still issues that we have to deal with in these kinds of cases. There are other advantages to Lebesgue's approach as well. Fortunately, they only apply to some really complicated examples. So it becomes very important later on using Lebesgue's approach instead of Riemann's. But whenever Riemann's definition works, whenever it is well defined, it agrees with Lebesgue's. Lebesgue is just more general. The reason we don't teach Lebesgue's method here is because, frankly, for most examples, like just about everything we do in this class, it doesn't matter. And Lebesgue's technique requires a lot more technical background to make sense of. So that is one method. You could try sort of throwing away Riemann's entire approach to the definite integral and starting again with another kind of approach. But the other thing that we could do is we could say, okay, in a situation like this, why did I erase this? I want this still. There we go. That integral is back on there now. What do we want to do is we want to say, okay, maybe we can't make sense of this in terms of Riemann sums, but maybe we can still make sense of this in some way, because what I could do is I could ask, well, what about in this first case, if I look at the limit as b approaches infinity of the integral from 1 up to b of, in this case, 1 over x squared dx, but in general, we could ask whatever function we're talking about. See, if I fix b as some very large number, no matter how large that number is, I can make sense of this integral in terms of Riemann sums. And if I can make sense of these integrals in terms of Riemann sums, then I can ask, well, what happens in the limit as b approaches infinity? For this second case, I can say, well, the problem is really going all the way to 0. If I do, and let me write this down and we'll see why in a moment. If I do the integral from a up to 1 over square root x dx, this is fine, provided that a is strictly larger than 0. So can I make sense of this by asking what happens in the limit as this lower bound is a positive number that's shrinking towards 0? And the answer, once again, is yeah, there's a good chance I'll be able to do that because I can make sense of all of these integrals. As long as a is a positive number here, I can make sense of these integrals in terms of Riemann sums. And then I can ask, well, what happens to the limit as a goes to 0? Now, whether we can figure that out or not, that's another question. Whether it comes out nicely or not, that's yet another question. But we can at least ask the question of, does such a limit exist? And integrals defined this way, these are known as improper integrals. Now, the thing is, these improper integrals are actually really important because taking integrals over things like the interval from 0 to infinity or from 1 to infinity, this is actually something that becomes very important in a lot of applications in things like statistics. Often in statistics, you're dealing with distributions that they tend to have long tails, often infinitely long tails, at least in theory. And because of that, we want to be able to deal with integrating these distributions, these statistical distributions. We want to be able to deal with those, and we need to be able to deal with them as they go through their long tails, okay? So these improper integrals are really important there. They're also important in things like physics. Often in physics, we do in fact need to deal with integrating over unbounded intervals. And similarly, in all of these cases, we do sometimes have functions that are not bounded. So the idea behind this is an improper integral is when we define an integral as a limit of proper Riemann integrals. And we saw two examples of that, right, that I wrote down before I had to erase them to put this on the board. So one of those examples was, we need to do the integral from 1 up to infinity. So the problem here is that our interval isn't bounded above. So what we do is we introduce an upper bound, and then we take the limit as that upper bound gets larger and larger as it goes to infinity. The other case was where the function was unbounded, and so what we did was we introduced a cutoff at the bottom, right? That was when we did the integral from a up to 1 over radical x dx. We introduced this cutoff, and then we ask what happens as the cutoff approaches 0. So in both of these cases, what we're doing is we're defining the definite integral. We're defining that in terms of a limit of proper Riemann integrals. And we're calling them proper here because they're defined in terms of Riemann sums. Now, the nice thing is that it's usually not super bad to do, well, it can be bad because we could be dealing with some really nasty antiderivatives, but in many cases, the antiderivative is not that difficult to compute, and the limit may not be so bad to compute either. So let's just write down a few examples, because I think seeing these examples will make it sort of clear how we do these problems in general. And once you see a few examples, you'll start picking up the hang of really doing these things. So let's suppose that I need to do the integral from 0 up to infinity of e to the minus x dx. So what is this going to be? Well, this is going to be, in terms of an improper integral, this is the limit as b approaches infinity of the integral from 0 to b of e to the minus x dx. Now, this is actually something that we know how to take the antiderivative of. This is just going to become the limit as b goes to infinity of negative e to the minus x evaluated from 0 up to b. And that is going to be the limit as b goes to infinity. So I'm going to tell you right now, the annoying thing about these problems is having to continually write limit as something does something throughout all of these steps, because it does go on. We're going to have negative e to the minus b plus e to the 0, because the negatives cancel there. So careful about the signs. Now the thing is, as b approaches infinity, e to the minus b approaches 0. So that part goes to 0, and we are left with e to the 0, which is 1. This has no dependence upon b, so in the limit, this just comes out to be 1. This is actually a really beautiful result. And think about what this means, sort of geometrically. What this means is I can interpret this integral as, if I look at the graph of y equals e to the minus x, it looks something like this, right? It goes through the point 0, 1, and then it keeps on descending like this. What this means is that the area under this curve in this region is actually equal to 1. So we have an unbounded region. This region keeps on going to infinity. But, and this is crucial, it actually only has a finite area. It has an area of 1. And that's really quite incredible. Now, you might wonder, like, what does it even mean to talk about this area? Well, what we mean is that if you cut off this, you can keep on cutting off this region further and further out, and you will never get an area that is larger than 1. Contrast this to, let's say, a rectangle that goes off infinitely in both directions. So, in other words, just a strip. Well, as I go further and further out, if I cut off this rectangle, I get larger and larger areas. I can make the areas arbitrarily large. In this case, if I take this region, no matter how far out I go, I can never make the region that I have bigger than 1. So the total area, it makes sense to say that total area is 1. We're going to come back to seeing a bunch of other examples like this, and it seems kind of paradoxical when you first encounter it. But it turns out that it makes sense. It really, there's no contradictions here in talking about an unbounded area or an unbounded region with a finite area. So let's try doing a similar example, and I want you guys this time to take a minute before I work the example and work on the example yourself and see what you can do with it. Try doing this time the integral from 1 up to infinity of 1 over x squared dx. All right, were you able to work this out? So here's the first step. We want to do this as the limit as b approaches infinity of the integral from 1 up to b of 1 over x squared dx. And I can actually write 1 over x squared, that's really x to the minus 2. That makes it a little easier for me to do the antiderivative here. So this is going to be the limit as b approaches infinity of negative x to the minus 1 evaluated from 1 up to b. So what is this? Well, this is the limit as b approaches infinity of negative 1 over b plus 1 over 1. Once again, that first term goes to 0, and hey, we just got that this is an integral that comes out to 1 as well. Kind of interesting that that happened. So we've just found another region here. I mean, think about what this means. This is the region that is under the curve 1 over x squared from 1 up to infinity, and it comes out to have an area of 1 as well. So, another example like this. Now, we can kind of generalize this kind of problem. We could ask ourselves, what happens with the integral of from 1 to infinity of x to the minus r dx? Well, what's going to happen with this thing is we're going to get the limit as b approaches infinity of the integral from 1 up to b, x to the minus r dx. This is going to be the limit as b approaches infinity. Now, here's where we need to be a little bit careful, right? So, if we take the case r not equal to negative 1, then this is just going to become x to the negative r plus 1 divided by negative r plus 1 evaluated from 0. Why am I putting a 0? From 1 up to b. And this is going to become the limit as b goes to infinity of negative, let's factor out the r plus 1 here. So we're going to have 1 over 1 minus r times negative 1 over x to the 1 minus r, or I'm sorry, r is not equal to 1 here. And then we're going to have, well, plus 1, really. Because when we plug in a 1 here into this, we just get 1 to some power, and it just has this factor in it. So what's going to happen here is that if 1 minus r is less than 0, and this is the same thing as saying that r is bigger than 1, then this is going to approach 1 over 1 minus r. Whereas if 1 minus r is bigger than 0, which means that r is less than 1, then this term is going to blow up, and this is going to be a divergent limit. It's going to diverge to infinity. So an interesting thing that we have seen here, in other words, if we're talking about x to the minus anything smaller than 1, so x to the minus 2, x to the minus 3, x to the minus 1.001, this integral converges to a finite number. But if we're talking about anything where this negative r comes out to be bigger than -1, well, in that case, this diverges. And what happens if r is actually equal to 1? Well, in that case, we have to do this antiderivative in a slightly different way, don't we? Because in that case, what we're really dealing with is the limit as b goes to infinity of the integral from 1 up to b, 1 over x dx. And this is going to actually be the limit as b goes to infinity of log absolute value x evaluated from 1 up to b. And this is going to be the limit as b goes to infinity log b. I can get rid of the absolute value because b is going to infinity, so it's positive, minus log 1, which this, of course, is just 0. But log of b diverges to infinity, so this also diverges to infinity. So what we have seen here is that the behavior of this definite integral differs very much depending upon the value of this exponent. For certain values of the exponent, what we're going to get is this nice finite 1 over 1 minus r business. For other values, we're going to get a divergent integral here. So we get this sort of behavior change when the exponent is -1. Now, that's also interesting geometrically because if you think about this in terms of areas, it means that if you're looking at the area under y equals x to the minus r, from here, this area is actually a finite area for certain values of r. In other words, when this exponent comes out to be less than -1. But once we hit -1 or above, then this area turns out to be infinitely large. So it's a very interesting bit of behavior there. Now, what happens in the other sorts of improper integral cases? Like, what if I need to make sense of the integral from 0 to 1 of 1 over radical x dx? Well, I can think of this as the limit as a approaches 0 from the right, integral from a up to 1 of x to the minus 1/2 dx. So this is going to be equal to, and maybe you want to pause this for a moment and see if you can work this out yourselves, but this is going to be the limit as a approaches 0 from the right of 2 x to the 1/2 evaluated from a up to 1. And so this is going to be the limit as a approaches 0 from the right of 2 times the square root of 1 minus 2 times the square root of a. This goes to 0, and this just approaches 2. So we end up with an answer of 2. Now here's a little bit of an interesting puzzle for you. Can you work out the conditions for the integral from 0 to 1 of x to the r dx to converge to a finite result? It's pretty similar in some ways to the example we did with x to the minus r going from 1 to infinity. Once again, you're going to see that for certain values of r, this is going to converge. For other values of r, it's going to blow up to infinity. So, yeah, again, it's just a somewhat interesting sort of thing here that we're looking at where we can get very different behaviors even though we have rather similar looking problems to begin with. Now, there's another sort of question that we can ask ourselves, like, what if I wanted to do the integral from minus infinity up to positive infinity of some function? Well, the way that we make sense of this is we say, okay, this is going to be equal to the integral from minus infinity up to 0 of f of x dx plus the integral from 0 to infinity of f of x dx. In other words, we split this up into two separate pieces. And then what we can do is we can say this is the limit as a approaches minus infinity, integral from a up to 0 of f of x dx. And this second integral can be defined as the improper integral limit as b approaches infinity, integral from 0 up to b, f of x dx. So in other words, if you have to integrate something over the entire real number line, you can do that. You just split it up into these two separate integrals like this, and then you do each one separately and you calculate the limits. This is the kind of thing that crops up rather frequently in some applications in statistics and other types of problems. Now, the thing is, though, that a lot of the most interesting cases, it's very difficult to actually compute or impossible to calculate these antiderivatives. So you end up needing to use other clever techniques for doing this kind of thing. But in general, you can do these problems by just splitting this apart into two different pieces. And I will let you take a look at the example in your book of doing this in a particular case. It's really very similar to the stuff that we've seen before. The other thing is that